Hi, welcome to today's lecture about zero knowledge proofs. Sorry for the late recording. I ended up recording the entire lecture without audio last night and didn't realize till I uploaded. And so I had to re-record it. But all is good now. Okay, so let's begin. Start with the overview. And I'd like to also start with some intuition. So I'd like to ponder for a moment on this question of how can we prove a statement X is true without resorting to revealing anything other than a statement itself is true, without resorting to a trusted actor as well. So that's kind of an abstract question, and I think it would be good to ground us in some examples. So, for example, we've all played the Where's Waldo game, and in the Where's Waldo game, we have a bunch of small people, and we'll make them all these little circles. And one of these circles is Waldo, and we'll make Waldo blue. Now, normally there's about 100 of these in the entire thing, and it's not so much blue as it is just a slightly different shade of red. And how do I prove that I know where Waldo is in the Where's Waldo game without telling everyone else who I'm playing the game with where Waldo is? Well, this is actually a really interesting example that I saw in a video on YouTube explaining zero knowledge proofs at 5 different levels. And this was, I thought, one of the really powerful examples that he used. So I guess take a moment amongst yourself and just think about how you would prove you know the location of this particular ring without revealing this ring's location to anyone else. Okay, that should give you enough time to maybe ponder about this while you paused. The way the professor suggested you do it is he suggested you build a giant, giant box. And the benefit of this giant box is the box is so much bigger than the rest of the game that you can't really tell where the game is with respect to location of the box. And you can carve out a tiny little hole right here. You can make a tiny little hole in this box. And what that hole will do is that hole can reveal the location of Waldo. So imagine, if you will, wow, I'm having trouble scrolling today. Imagine, if you will, that, okay, imagine, if you will, that hole itself has opened up. Sorry, one moment. My computer froze. So yeah, we have this and we had that large black box. Imagine there's a little hole going right over here. Since the box is so much bigger than the rest of the game, we don't really know where the hole is relative to the box, right? We don't know if the box is here, right? The game could be placed here, it could be placed here, it could be placed here, and it could be placed here. So when we cut a hole to reveal the location of Waldo, that hole doesn't really tell us any information about where Waldo actually is. So that way we've revealed that we know the true location of Waldo, but we have not revealed where Waldo is in the game to anyone else. So that's like maybe I find that to be just a very simple example that helps me conceptualize zero knowledge and the potential power of zero knowledge. So let's go with another couple of examples to kind of hammer this idea home. So how do we prove that a child is tall enough to ride a ride at an amusement park without revealing the child's true height, hair color, etc.? So I'm sure we've all seen at some point in maybe a movie, right? It's like the ride used to be this tall to ride. And then you have the little kid show up, and the little kid is maybe like here. And the way the kid reveals how tall they are is they stand next to this little measuring tool, and that tells you whether or not you are tall enough. Well, this is a little bit wrong, right? Because one, we're revealing the child's true height. You're revealing the child's hair color and other personal identifying attributes to this attendant who only needs to know that they're above a certain height, whether it's 5 feet tall or some other height. And so another way of accomplishing this is you could have the child uh, write down their height and have it be the child could just write down a plus or negative sign. If they were above, if they were greater than or equal to, or lower than this height after measuring themselves in like a private room. And then the person could go in and they could see that plus or minus sign. And that would tell them whether or not the child was tall enough to ride. I mean, you're trusting the child there to act honestly, and it's not a very elegant example, but that would be a somewhat of a zero knowledge system. So that's not that this example I just gave you is not a true zero knowledge system, but I think it helps get the idea across. The last example, how can we approve that you can afford to buy coffee without revealing your net worth, your bank account total, preferred currency, etc. Um, so with this one, right, like when you swipe your debit card to buy something, you know, how do we tell that vendor that you can afford to buy that item without either having the trusted actor, the bank, tell them you can afford it, or without having to show the bank teller your actual bank balance? How can we develop some system that allows us to do that? These are the kind of questions that we can solve with zero knowledge proofs. And then maybe one example, right, related to RSA security. How can we prove that n is the product of two primes, p and q, without revealing its factorization, right? How do we prove this without factoring in and giving away what p and q are? Because if we gave away p and q in RSA, that would compromise security. But we also need to prove, right, if you're still able to prove that n is a product of two primes. That's another example of how we might use this kind of technique to our advantage in cryptography. So some definitions. What is knowledge? If you're thinking about zero knowledge, having a clear definition of knowledge is going to be very important to making sure that we know what we're referring to when we say quote unquote zero. And so in cryptography, we refer to knowledge as things that can be computed efficiently. If you go back to our previous example right here, n is a product of two primes p and q. Well, if you know n and p, you effectively know q because you can efficiently compute q from n and p. Even though you don't have q written down, you still quote unquote know q. So it kind of follows from this definition that a zero knowledge protocol is a protocol that doesn't reveal any information that the adversary themselves could not otherwise efficiently compute, right? So if you have some secret and you let's say you have some secret, let's say X is your secret, right? And the adversary knows the encryption of X, and the encryption of X is C. Well, everything the adversary knows, aside from public parameters, can be boiled down to what they can compute from C. And so that's going to be a very important central concept when it comes to thinking about zero knowledge throughout. And if you had a protocol that proved that you knew that M and C, that if you knew that the M, let's say we had a protocol that proved you knew the M that is C encrypted, right? So back to our previous example, what if you had a protocol that proved you knew that C was the encryption of X? You wouldn't want to reveal any information that the adversary couldn't already easily compute from C directly, right? You wouldn't want to reveal anything that the adversary didn't already know about C. So some examples. Um, the Alibaba cave is maybe the most famous example of zero knowledge proofs. So we have our two friends and protagonists, Alice and Bob, and they're on an adventure. And on this adventure, they stumble onto a cave. And at the cave, there are two different entrances to two different paths. And there is a door somewhere in the cave connecting these two paths. So let's kind of draw this briefly, right? So we have entrance 1 and we have entrance 2. And from entrance 1, there's a path doing something like that. And from entrance 2, whoops, there is another path doing something like that. And right here, there is a door that connects both of these paths. And interestingly, Alice knows the code of this door in blue and offers to sell that code to Bob. However, Bob is not a chump. Bob wants to know that this code works before he pays Alice for the code. And Alice doesn't want to give the code to Bob without Bob purchasing it first, right? I mean, you don't want to give away your secret without, making some money off of it. So Bob offers to follow Alice into the cave and then close his eyes while Alice taps in the code. But it's dark in the cave, and Alice has no way to actually be sure that Bob has his eyes closed. And while we might want to trust Bob, that's a trusted actor in cryptography. We're trying to find systems that are stronger than that, right? We should have a system where even if Alice and Bob don't trust each other, they can safely have confidence that Alice knows the code, so that way Bob can pay for the code. So, our two friends are at an impasse, but then their hip friend Suhail wanders by, fresh from his introductory to cryptography lecture, and offers a solution. So if any of you watch this lecture and then go on a hike and find two people at a cave, this is the scenario you might find yourself in. Who said computer science does not have real world applications? And Suhail suggests that Alice picks any one of the paths to enter into the cave. And then Bob, who doesn't know which path Alice chose, can call out which path he wants Alex to exit from. So imagine this, like Alice picked, let's say Alice picked A. Bob doesn't know that Alice picked A, and Alice disappears into the cave. And then Bob calls out which path he wants Alice to exit from. Now, there's a 50% chance that Alice and Bob choose the same path, right? So let's look at those odds mathematically, right? So we'll have Alice's choices be here in the black. Alice can choose A or B. And Bob can choose A or B. But Bob has this this to contend with. We'll make Bob blue. So what happens is, right, Alice chooses A, and then if Bob chooses A, they've chosen the same path. If Alice chooses B and Bob chooses B, they're still on the same path. So half the time, at random, they're going to choose the same path. Then the other half of the time, they're going to choose different paths. And it's unlikely over multiple runs that they choose the same path. And at the end of the run, they will each learn the path that Alice, they'll learn, even though Bob is not learning which path Alice chose at the start, if we do this, 10 times, and Alice emerges from the correct cave each time, then it's unlikely that they repeatedly chose the same path 10 times. So then Bob has a statistical degree of certainty that Alice chose the same path. Now, I know some of you are thinking right now, you're being silly. Why doesn't Alice just enter in A and exit in B? And that works, but something that's common in cryptography is this idea of statistical certainty. And this method, even if Alice was acting maliciously and somehow picking a path, like what if Alice lied to Bob, said, okay, I'm going to go in A, and then said, Bob, look, there's a bird, and then wandered into B, right? Like even let's say that happened. Well, then Alice as a malicious actor can trick Bob in that previous schema. But in this schema, even if Alice is a malicious actor, there's no way she can trick Bob repeatedly, right? Because this scenario actually guards against a malicious actor in a way that the more quote unquote straightforward scenario does not. So that's kind of maybe another toy example to get us thinking about zero knowledge. Now let's consider a maybe more real example of how zero knowledge might be used. So recall from last lecture the discrete log problem. Not from last lecture, from a few lectures ago, this discrete log problem, right? The discrete log problem says if you have a if you have if you have a group G and you have G to the X, taking the discrete log of G to the X over G is like really hard. That's the discrete log problem. Um, so how can we prove that we have knowledge of discrete log without revealing the answer, right? So let's set it up. So we have our prover. So all proof systems will follow this format, right? We're going to have a prover and we're going to have a verifier. And the goal is for the prover to prove that you know X such that H equals G to the X, assuming G and H are in G. That is what P is trying to prove to V. And you want to prove this without revealing X. Now, I'm just going to let you take a moment and think about how you might want to solve this problem. So normally we'd pause here for 3 minutes of class. So maybe pause the video and think about this and try to arrive at an answer. Okay, that should give enough time to pause the video. Um, Find my place in my little slide deck. Great. So we start out with the prover sampling a random number r from the positive integers bound by p. And this r we know is within, like this r we know. And then we're computing u, which is equal to g to the r, right? And g to the r is within the group G. The prover then sends u to the verifier. This way, yep, so it sends u to the verifier. The verifier then sends C, it samples C at random from ZP. So the prover made one random sample, the verifier made another random sample. And it sends C back to the prover. Notice it's important to note here that this verifier did not send G to the C back to the prover, it just sent C back. And the prover then calculates Z, which equals R plus C to the X. And it sends, oh, that should actually be sending U back. So it should be sending Z back. So that is Z. And the verifier then verifies that G to the Z equals H times U to the C. So does that follow? Does that make sense? Well, let's kind of write something out there, right? Oops. So h times u to the c equals g to the x times g to the, oh wait, let me just, I think I switched these around, equals r times, oh, this is to be u times h to the c. Sorry, let me correct this slide just to clear up any confusion that I've created. So what we care about is they send z over here, becomes z, this becomes, instead of being h times u to the c, this actually becomes this will become u times h to the c. Okay, so let me just quit preview and reopen the code. All right, sorry about that. So we're back where we are, right? So the prover randomly samples R, sends U equals G to the R to the verifier. The verifier samples C and sends that back over. And then the prover computes Z equals R plus C to the X, sends Z over. And then the verifier verifies that G to the Z equals U times H to the C. So how does that, what does that math actually shake out? Does that actually work out? Well, let's look at the math. G to the Z equals U times H to the C, which equals, what's U? U is G to the R, times H, which is G to the X to the C, which equals G to the, and then this is all kind of basic algebra, remember, R plus XC. And this equals Z. So G to the Z does in fact equal this. And how does this prove knowledge of X? Well, there is no way to compute Z unless you know R, you know X, and you know C. Well, the prover randomly sampled R, and the verifier randomly sampled C. So really, you have to know X ahead of time to complete this proof successfully. And in this proof, you proved one of two things, right? Either you proved that you know X, or you proved that you can take the discrete log of over the group G. And since we know taking the discrete log over the group G is like really, really hard, then it's much more, you just definitely know X. If you can take the discrete log, I will give you an A plus in the class, uh, and I will throw in a PhD and maybe a Turing Award as well. Like that is probably one of the hardest problems, and I'm pretty sure it's NP. Um, so if you can solve this in polynomial time, then you know, congratulations, you have revolutionized computing. But until one of us does that, we're going to assume that that is pretty much one of the hardest guarantees we can make. And so, returning to this proof, by solving this problem, by showing this problem this way, what we're demonstrating is we're demonstrating that you must have knowledge of X in order to compute this value Z, such that U times H to the C equals Z. So that's maybe a very practical knowledge of zero knowledge in a cryptography setting. That's going to come up again in a few minutes. But let's talk about, okay, we'll talk about this record. So let's talk about the discrete log zero knowledge authentication protocol. So what if an adversary has hacked the server and can see clients' interactions with the server as well as they can see the data on the server? Now, any non-zero knowledge interaction will lead to compromised identities for people who try and log in. And however, if the storage stores G and G to the X, and the server and client complete the zero knowledge proof without ever revealing the client's secret X, this would accomplish a zero knowledge authentication, right? Like if you can do this, you have proved knowledge of X, and the verifier does not know X. Only the prover, that's you, knows X. So that's an example where you can actually use this as an authentication protocol if X is the password. So I know there's all kinds of cool hip nightclubs in New York. How cool would it be if a nightclub said, you need to do a zero knowledge protocol to prove to me that you know the password X? I think that would be pretty cool. Uh, and maybe that shows how often I go to nightclubs. Okay, so that's kind of another zero knowledge authentication protocol. Something to think on is later in the later in the lecture, we're going to talk about um, non-interactive zero knowledge proofs. And we're actually going to transform our discrete log protocol into a non-interactive proof. And it'd be good for you to think about how you might do that throughout the rest of this lecture in the back of your head. So what are the properties we care about for zero knowledge? Well, all zero knowledge proofs, right, are proof systems. And the goal of a proof system is to convince a verifier that a statement is true. And that results in these kind of few properties. One is completeness. An honest prover will be able to convince a verifier of all true statements in a good proof system. And a good proof system, a dishonest prover cannot convince an honest verifier of a false statement. And if you add interactiveness and randomness, that will enable a proof system to do zero knowledge. In fact, did I mention this? Yeah, okay. So that's kind of generic proof systems. Um, Notice there's nothing in here about the number, you know, there's nothing in here about the complexity of the problem. This is just general proof systems. And with zero knowledge proof system properties, well, what are those extra ones? Well, for something to be a zero knowledge proof system, we need to be able to construct something called a simulator. And the intuition behind a simulator is that anything a verifier can learn from a prover, they should be able to learn by just running a simulator. And the more precise definition is that the distribution of interactions with the prover needs to be indistinguishable from the distribution of interactions with a simulator. Now, what does this kind of mean? This means that the simulator reveals nothing that is not already computable. And since they're revealing nothing that is not already computable, then they are revealing, and then that means that the actual protocol itself reveals nothing to the to the it reveals nothing to the verifier that's not already computable. And this is like kind of remarkable. I mean, this is like, imagine I could prove to you that I can unlock a house, and I do it in such a way that you can run the simulation of me doing that proof a billion times, and you can watch me do the proof a billion times, and you will learn nothing about how I can actually unlock a house. That is like a pretty incredible definition and property. So this simulator thing is quite interesting. And a really interesting zero knowledge property is that if we actually have true one-way functions, right? One-way functions, remember, if we can actually map from some group X to some group Y, then any proof can be proven with zero knowledge, which is pretty cool. So if you want to make a lot of money, solve that problem. So that's kind of the zero knowledge properties and the proof system properties. Let's go to one more example and talk about the three-color graph problem. And let's apply these properties to the three-color graph problem. So the three-color graph problem is, can you color a given graph such that no adjacent vertices share the same coloring? So what does that look like? Well, let's make a pretend graph. And these are our vertices. And these vertices are connected by edges. Now, can we color this graph such that no adjacent vertices share the same coloring? Well, if I make, whoops, if I make this one pink and this one pink, and I make this one blue or purple, and I make these last two green. Well, then I've colored this graph with three colors such that no adjacent vertices share the same coloring. So actually solving this is the three color graph problem. And to solve the three color graph problem, we need a cryptographic primitive called commitments with two functions. Commit, which takes public parameters, which are just an empty space in this example, and a message m, and produces a commitment and an opening. Think of a commitment as some kind of like sealed letter. And you can think of the opening as the only way to open the sealed letter. And the verifier takes those public parameters, the message, the commitment, and the opening, and verifies that that commitment and that opening correspond to that message under those public parameters. So that's what a commitment scheme is. You actually, on a homework assignment, might be asked to generate a commitment scheme. Um, and this scheme has to have a few properties, right? It needs to be correct, so it needs to obey the Shannon correctness, uh, Shannon correctness requirement. It needs to be hiding. The adversaries must not be able to distinguish which commitment corresponds to which message. So that's 1, 2. And then lastly, it needs to be binding. The same commitment, the probability that the same commitment works for the same message, the probability that a commitment works for multiple messages and openings needs to be negligible. So those are kind of requirements around the commitment system we're going to use to solve the three color to do a zero knowledge transfer of proving you've solved the three color graph problem. So you have a prover and a verifier, and let's assume that the prover and the verifier, let's assume they both know the graph G. And the prover has to do a few things, right? First, the prover has to arrive at K. Let's say they know K, and K is a valid coloring. And just recall that a valid coloring is some coloring such that no adjacent vertices share the same coloring. Then the prover is going to scramble up the colors by permuting them, and it looks like a random permutation. So if you recall, we used pink, blue, and green. Well, what's going to happen is the prover is going to generally make a little scramble such that, pink might get turned into yellow. Let's say pink becomes yellow. Let's say green becomes this like very deep purple. And let's say blue becomes red, right? Effectively, my coloring hasn't changed. I'm just using different colors for that coloring. That's what we mean by the permutation. And then the prover is going to commit to that coloring. Then the prover they don't send you, sorry, they actually send um, the commitments. So this is not you. You need to fix that. This is actually CI, comma, R. I. Okay? And the verifier samples I and j from the samples an ij pair from the edges. So I is the initial node, j is the second node, and a node is defined, sorry, an edge is defined by the two nodes that it connects. And then it's going to send I and j back to the prover. And then the prover sends the opening sends the coloring for I and the coloring for j along with the opening for I and the opening for j. And then the verifier takes those public parameters and verifies that the color for I is the color that the prover committed to up here. So just to color that out again, this is not U, rather this is C, I, comma, R, I, comma, for all of them. So the prover commits to these colorings, the verifier asks for an edge, and then the prover sends the coloring for that edge, and it sends the openings. And then the verifier just verifies that those in fact are valid colors for those openings, and that I does not equal j. And then they repeat this as many times as they want to. So the prover will then recompute a new color permutation and then commit to those new colors, send those new colors to the verifier. The verifier will then send a different edge, I and j, and then the prover will send back the colorings for the new edge and the new openings, and then the verifier will verify that those are real. So that's how this is how the system works. So you can imagine essentially what's happening is the prover says, okay, I've sampled my colors. Tell me what edge you want. And the verifier asks for an edge. And then the prover says, aha, that edge is green and red. And then sends that back to the verifier, who makes sure that it really was green and red based on the commitments. And the verifier says, okay, let's do this again. And then the prover says, okay, let me just rescramble my colors. And they rescramble their colors and then do it again. So you could conceivably check the edges, and there's no way that the verifier, that the prover commits the verifier of their knowledge. Now, what is the probability? Now, what happens if the prover does not have a valid coloring, right? Well, let's say there's only one miscolored edge, right? The probability that the prover succeeds is 1 minus 1 over the size of the edges. That's if there's one missing one. However, if you just run this proof, something like, let me look at my notes. If you run this proof enough times, that probability that sneaks by starts to shrink. More specifically, if you repeat this something on the order of E of the number of edges squared, the probability that you can prove a false statement becomes roughly it becomes roughly e to the minus m, I believe. It becomes a negligible probability. So by repeating this protocol enough times, this somewhat small chance of tripping up the prover actually becomes quite a large chance. So that's the three-color graph problem. Another really, it's honestly, I think, my favorite example next to discrete log. So let's talk about Schnorr signatures. Their signature, digital signature, so the verification key is G and G to the X. And to sign, you use a non-interactive version of discrete log of X, where the challenge C is derived from the message using a hash function. Okay, So I remembered early in the lecture, I mentioned that we'd be talking about this. So let's go back to early in the lecture and go here. So we're talking about a non-interactive version of this. So what would it take to make this non-interactive, right? A one-shot proof. Well, really, the only thing the verifier does is send this random value C. And if we have a hash function, right, and we can generate C from a uniform random distribution such that the hash of some message M is like equivalent to C, we can do that, then that would give us then the prover could just, instead of receiving C from the verifier, could just say C is the random grab of this hash function. And this way, the prover can just send U C Z to the verifier, who could then verify all of these, could check that C is in fact a hash of the message M, and then check that, ultimately check that G to the Z equals U times H to the C. So that's what a non-interactive zero-knowledge proof kind of looks like. We'll do more of those next week. And so this is actually used in practice, and it's something very similar to it called DSA or elliptic curve DSA. We can talk more about that later. So let's talk about failed implementations, good warnings to humble us as cryptographers. So for PlayStation 3 updates, and actually some Bitcoin wallets, the updates are signed using Schnorr signatures. And with these Schnorr signatures, these are these signatures that we kind of discussed up here. If this R is not sampled well, this little R right here, if that's not sampled well, things get very insecure very quickly. And uh, notably, some systems derived randomness from a fixed constant. And this allowed hackers to discover that fixed constant and then deploy arbitrary firmware because they could sign that firmware as legitimate coming from PlayStation. Or you can imagine for Bitcoin, uh, send valid transactions from that wallet, which is no good. So, what's the lesson here? The lesson is avoid reusing your randomness. And that's lecture for today. Thank you so much. This is probably my favorite topic in cryptography. So, and there's a lot packed in here, and there's a lot of detail. And so I would just take a moment and maybe review this lecture once or twice. On the final exam, if we do a final exam, there will certainly be some complex homework, some complex questions, I'm sorry, related to this. All right, thank you so much.